Hello, this is Dr. Hasan Abdullah with the course Analysis of Algorithms. And the topic which we are covering is Advanced Algorithms, which is the 12th topic in our topic list. And the subtopic is Approximation Algorithms and Genetic Algorithms. So this video is developed using the supplemental material available at www.easymcq.com/GoGet. So this basically is a learning management system. To be more specific, it is a personalized learning management system because it allows you to set the direction, the route, and the pace of your learning. How you do that, that is shown in video number 1. And of course, this also allows you to achieve this by using searchable keywords which preserve the order of the results or which is free order of the keywords. Again, how you do that, that's shown in video number 3. And to enhance your learning experience, you can personalize how the interface looks and feels. And of course, you can also perform self-testing and self-knowledge acquisition testing, having online testing, which is done online grading, and the results are analyzed of all the exams and the quizzes you have taken. How you do that, that's shown in video number 4 and video number 5. So where are all those videos? Those videos are available on the course website, which I'll just show you. They are also available on my YouTube channel. So you go to YouTube and type my name, Dr. Hasan Abdullah, and they're also available on Canvas. So now we go to the list of the course topics, and right now we are at the topic which is the advanced algorithms, and the subtopic is approximation and genetic algorithms. Now there's a complete course on advanced algorithms which I also teach, but this is going beyond this limited material is going kind of beyond the scope of this course. So let's move on to the supplemental website. So in the video 12a we covered randomized algorithms. So now we move on to the approximation algorithm. So why do we need approximation algorithms? Because the intractability of exact solutions, the solutions to the problem which you are looking for, they are not tractable. Okay, but we would like to have solutions to these problems. Of course, not the exact solutions. So that's the one reason. Complexity of the optimization problems, the time complexity of the problems which we want to solve is so high that they are basically non-polynomial time in nature, and that will take huge computational resources which are not available. Therefore, we have practical time constraints which we need to meet. So this is the reasons why, one of the reasons why we use approximation algorithms. For example, the traveling salesman problem or the traveling salesperson problem or the knapsack problem, they're NP hard problems, which means that there are no efficient algorithms which can work on real problems. Okay, and as the problem size grows, right, it becomes computationally very prohibitive, and it is not tractable to solve those problems. For say problem size 20, 30, 40, which is small size, then it becomes intractable. So, and of course, finding the exact solution is practically impossible for large instances. So we are kind of stuck here. All right. So one is the intractable nature of the problem, and then is the complexity of the optimization problem. For example, graph coloring and maximum independent set, and so on. And then we have the practical time constraint. So we have covered all of this in the part 12a of advanced algorithms for this topic. So let's move on to the second reason, or the second part, why we need approximation algorithms. What is beautiful about approximation algorithms is that we can provide guarantees of how close the solution that is provided with reference to the optimal solution. That's one of the beauty of approximation algorithms. And handling large scale problems, since we are not going towards the exact solution, right? So we are not going to hit by the intractable nature of the problem itself. So we can address large scale problems with the problem size is very large, obviously, and that allows us to solve real world applications, real world problems. allows us the Allows us and provides us the flexibility. Flexibility means that we are not constrained by the exact solution. So for example, we have a two approximation algorithm. What does it do? It guarantees that the solution will be no worse than twice the optimal solution. Now these guarantees have solid proofs, okay, and they are essential because they provide a predictable quality of the solutions. Remember that for a heuristic, there is no bound, there is no guarantee about the predictable quality of the solutions, which is not the case over here. Okay, and it is crucial for many fields, for example, scheduling, for example, routing, for example, operations research, and so on. Right? So we need to be aware of the worst case performance before implementing a solution so that we are not kind of jumping into darkness. Okay. Now, handling large scale problems, since we are not going towards the exact solutions. Okay. Why? Because they become computationally unfeasible, they are intractable. So, approximation algorithms is a practical alternative. Okay. And of course, they allow us to come up with quick and scalable solutions. Remember that these quick solutions are not guaranteed to be the optimal. So since they are not required to be optimal, so we can work with very large inputs, okay, and without requiring immense computational power, which are required by exact algorithms. Okay, as a matter of fact, that is the limitation of the exact solution. So let me clean this and move on to so flexibility in real world applications. These approximation algorithms are versatile. They are versatile, and of course, they can be tailored to suit specific real world requirements. So we, instead of going for the exact optimal solution, right, which is not achievable for even reasonably sized problems, therefore we go for a good enough solution. Okay, and we have certain constraints which are available to us. For example, constraints like the cost, constraints like the time, and the constraints like the resources. So in the presence of these resources constraints and time constraints and cost constraints, we adapt the approximation algorithms to these constraints, okay, which allow us the flexibility and ease of implementation to solve many of the complex problems which are real in nature. Okay, so what is the formal definition and guarantees of an approximation algorithm? So let's look at the formal definition, right? And these definitions will clarify the entire concept. So an approximation algorithm is designed to find not the exact solution to an optimization problem. Why? Because finding the exact solution is computationally infeasible. So they are designed to find an approximate solution, right? But it is not a heuristic. So what we are trying to achieve is to come up with a solution which is not the optimal solution, but which is close to the optimal. Okay. And how close? There is a guaranteed bound, right? There's a guaranteed bound. So that guaranteed bound is no worse than a certain factor of the optimal solution. So we know that it is, so if we're trying to maximize something, we know that it will be that much closer to the maximum result. And similarly for the minimization. So that bound is called as the performance ratio or the approximation factor, right? And that is denoted by alpha. So we can say, for example, depending upon the nature of the problem, we can say that the cost of the approximation algorithm solution is at most 1 over alpha times the cost of the optimal solution, right? So for example, we say that two approximation algorithm, okay, so it is guaranteed that the solution will not be more than twice of the optimal solution. So if it's the traveling salesperson problem, and say for example the optimum cost, okay, which is the minimum cost, is like say x, so we know that corresponding approximation algorithm can provide a cost which is not more than 2x. It could be less than 2x also, but not more than 2x. So what is the approximation guarantee? So the approximation guarantees provides what? They provide a formal bound, and that bound is rigorously proved also. Okay, and of course that ensures that the algorithm will be no worse than that bound. All right. So there can be a maximization problem, there can be a minimization problem. Okay, and that bound provides us the guarantee. Okay, and the confidence also that the algorithm will deliver a solution with a provably good range, meaning that the range of the quality of the solution has a rigorous proof. So there is no guesswork here. So the trade-off between accuracy and time complexity, the trade-off is that at the cost of quality, we are getting a solution quickly. Okay, and the cost is the accuracy. So of course, improving the approximation factor can sometimes increase the running time, and vice versa. So so we see that for a high time complexity, we can get an exact solution, but a simpler approximation algorithm runs faster and gives less optimal result. So what I'm trying to show here in this diagram, in this picture, is real data. And you can see that this real data is changing very, very fast. So you can see how much variation has taken place in 3 hours. Now, if there's an application which is running and it's doing algorithmic trading, so if I get a decision or a result to make a decision which takes me like an hour, okay, then that's not useful because things have changed significantly in an hour. So, of course, I'm living in an imperfect world, so I am depending upon my needs. Maybe I'm comfortable getting an imperfect result or imperfect answer within a reasonable amount of time. So then we kind of conclude with the genetic algorithms. So the genetic algorithm is very, very different concept with reference to what you have and what you may have covered earlier. So we'll talk about what are genetic algorithms. Basically, the genetic algorithms try to mimic the concept of the survival of the fittest. So the objective is to use that concept, map it to the optimization problem, and we try to mimic that the process of evolution. And the objective is to not to get stuck in the local optima, not to get stuck at the local optima. So what how it goes about? So there is a process of natural selection. Okay, so these genetic algorithms are inspired by the process of natural selection, and the solutions are joined together as the creatures kind of join together. I'll explain it, but that's basically it's multiple lectures which is not within the scope of this course. And then using parts of the solutions to evolve into better solutions, and of course trying to mimic the genetics. So what are genetic algorithms? So the genetic algorithms, basically what they do is they are basically optimization and search algorithms, right? So for example, I may be trying to I apply genetic algorithms for the traveling salesperson problem, say for example, okay, and they mimic the process of biological evolution, which of course has taken millions of years. All right, so how do they go about? So we have a population of candidate solutions, okay, like creatures, so to say, and over the generations using the operations such as selection and crossover and mutation. So we basically combine those solutions and get and hope and work towards better solutions, that is better performing individuals. Okay. So what is the process? The process first is the natural selection. So the organisms which are basic solutions that are better adapted to their environment are more likely to survive. Okay, and passing on their advantageous traits to the next generation. Okay, so we have the solutions which are better quality solutions as compared to other solutions, and we combine those solutions to create another family of solutions which are better than the previous ones. Okay, so we are basically simulating the fitness. So we pick the fittest solutions, those that best solve the problem. Okay, and which are the parents of the next generation of solutions. Okay, so the objective is that if we keep on repeating this, so this population evolve towards better solutions, meaning that they kind of get out of the local optima. So that's the objective. Don't get stuck in the local optima. So what is evolution? Evolution refers to a gradual change of population, a gradual fine tuning or improvement of the solution. And in genetic algorithms, this process of evolution is simulated. Of course, there is no real creatures, simulated by the iterative improvement, okay, of what of the candidate solutions over a period of time. And of course, that takes multiple generations. So one thing is clear that genetic algorithms they take time. So how do those genetic algorithm works? Because those solutions basically they evolve over time, right? They evolve over time, and how they evolve over time because we combine and recombine the solutions, and there is mutation also. Mutation is a slight change which is not based upon the combining and recombining. So the objective is that ultimately after like a lot of iterations we move towards the optimal, right, or the near optimal state or the solution. So remember that there it's not approximation algorithms, it's a whole new different technique. They are not randomized algorithms. Basically what we are trying to do is to simulate or mimic the process of evolution. So the traits are inherited from one generation to the next, as we see in our real life. So the good quality or the traits or the good quality aspects of one family or one generation of solutions is passed on to the next one. and they are represented as, this is how they are coded, as chromosomes, strings, or genes. And these chromosomes encode, so we have to basically map the problem into the form of genes or strings. And then we have, because why, because that's the way it works in the real life. And these genetic operators like crossover, recombining, and mutation, randomly altering the parts of a solution. Okay, so we used to explore the solution space. Again, the objective is to get out of the local optima. And the concept of inheritance, where the offsprings inherit traits from their parents. What are the traits? The traits are the good quality solutions. Okay, so here we have what it looks like. So we have this solutions. All right, so we have a1, a2, a3, and a4. All right, so what we further do, this is the way they are coded, as this is called as the string coding. So we have this is the gene, this is the chromosome, and this is the entire population. So we have this different creatures or different codings of the solutions, and then these combine. And as they combine, so this is a change in the values. Okay, and we have a new generation. And of course that new generation results into, as you can see, that we have a new creature which is based upon a1 and a2, which is a5. And we have, of course, we can have another creature also, because this is mutual swapping. So we have two new creatures, a5 and a6. Of course, the objective would have been to minimize or maximize something which was coded in the form of these string creatures. Okay, let me close this. Okay, so how does the genetic algorithms actually work? So actually, this is very detailed aspect. How do they actually work? So we start with the initial population, and there is a criteria for evaluating the fitness of the creatures. Then we select those creatures, the string creatures, from that population, and then we cross over, as I showed you before. So this is a crossover, kind of crossover, and recombine them, and we have a new generation of creatures which have the inheritance, which inherit the good qualities of the solutions of the previous generation. And then there's a mutation, which is a random change. Okay, again the objective is to get out of the local optimum. And then we replace the creatures some, and of course the size of the generation is correspondingly checked. And then we have a termination criteria. The termination criteria could be time, it could be the number of generations, number of iterations, or the difference in the quality of the solution with reference to the previous generation. This is explained, all of this explained here. And this is a block diagram. So we have this initial population, and then we score and scale that population. Scoring means you check the quality, and then we throw away those solutions of the creatures which were of not the right quality, and retain the elite creatures, right? And then we select the parents, and we have a produce crossover and mutation takes place, and it goes back, and this keeps on looping till we reach the terminating condition. So to end this topic and to end this course, this is the last question, the concept that contrast and compare randomized algorithms, approximation algorithms, and genetic algorithms. So here is a very, very detailed comparison, and I will just go over some of those comparisons. So let's look at the disadvantages. So the randomized algorithms may not give the correct results, especially in rare cases, which is the case for Monte Carlo algorithms. The disadvantage of approximation algorithm is that may not find an exact solution, only an approximate solution. Okay, we are never guaranteed the exact solution. And for genetic algorithm requires tuning parameters, no guarantee of optimal solutions, and it may take very long time, because remember that it took millions of years for the evolution to start and to reach the point where it is currently. So it's very time consuming. And then is the behavior. For example, behavior of randomized algorithms, outputs may vary with each run but gives good expected results. This is for Monte Carlo, and the quality of the results is guaranteed for the Las Vegas algorithms, but the time complexity is not guaranteed. Behavior of approximation algorithms is that guarantees a solution within a specific factor of the optimal. This is very good guarantee. So I know that how good or how bad I'm going to be, right? After spending a little time, right? And genetic algorithm uses selection, crossover, and mutation to evolve a solution over generations. So that can be very time consuming, and there are too many parameters to work with. You have to code it also, and so on. And finally, I finish it with the guarantees. that for the randomized algorithm, there are only guarantees which are probabilistic. For the Monte Carlo, of course, Las Vegas algorithms have a guarantee of correctness. For the approximation algorithm, they provide a provable approximation bound on the quality of the solution. Again, there is no guarantees, and there is nothing guarantee, none whatsoever for genetic algorithm. So that's all I have for this, and thank you very much.